Now let us discuss about coefficient of coupling. Okay, coefficient of coupling. So what do you mean by coefficient of coupling? Now here you see, suppose we have two coils. This is the primary coil. This is the primary coil. And another coil, this is suppose secondary coil. And due to mutual induction, there will be a EMF induced here. In the secondary coil, due to the current through the primary coil. This is primary coil. Secondary. Right? So let us consider that mutual induction, not mutual inductance, self-inductance. It must have a self-inductance. So that is suppose L1. And self-inductance of this, when current flows through this circuit, then magnetic field will be generated here, right, due to the current in this primary coil, and due to this magnetic field lines, and this field lines also pass through this. Okay, these are imaginary lines that field in this magnetic field in this coil may not be same as this, because the magnetic field associated with this or you can say flux associated with this or linked with this coil may not completely linked with this, right? So as for example, I have taken, suppose there are 10 number of lines of field lines, 10 field lines of magnetic field lines passing is generated here, and out of 10 maybe 7 or 5 may pass through this, or maybe sometimes it may all of them may pass through that. Okay. Depending how these two, how close they are and how are they set up, depending on that. So these are imaginary lines. Practically we can't see such lines. Okay, just in order to study the behavior of magnetic field, we need to imagine such lines, right? So now, due to change in current, when current rises from 0 to I1, there will be change in magnetic flux through this coil as well, and then there will be an induced EMF for which that current will flow in this circuit, and that current, because of that current, again there will be a self-inductance, so that is suppose L2, and flux linked with this primary circuit, suppose phi 1 or you can say phi p, and flux linked with this coil, secondary circuit or secondary coil, be suppose Qs. Then the coupling coefficient is the ratio of these two. That is the coupling coefficient. So that is given by K, which is the ratio of magnetic flux linked with the secondary coil to that of primary coil. Phi S by phi E. So this is what coupling coefficient. And also, if the mutual inductance of these two coils, suppose mutual inductance of this coil is suppose M. M is the suppose mutual inductance of the two coils. Then L1 is the self-inductance of primary coil. L1 is the self-inductance of the primary coil, and this is the self-inductance. This is the self-inductance. L2 is the self-inductance of secondary coil. secondary coil. So then this K is also given by M by rule over L1 into L by this expression. Now let us consider three different cases. Suppose two coils are arranged coaxially. Then in that case magnetic flux linked with primary and secondary coil, both for primary and secondary coil will be same. So in that case K will be equal to 1 because here phi s is same as phi p, right? Now let us consider a situation. Suppose this is the primary coil and this is the secondary coil, and due to the current in this coil, magnetic field is generated, and this magnetic field is not linked with this coil, this secondary coil. Then in that case coupling coefficient is 0, right? So this coupling coefficient K, its value lies between 0 and 1. It may be greater than equal to 0 or less than equal to 1. Remember that. Okay. So that's all about this coupling coefficients. So hope you have understood now. Now let us discuss about AC generator. Right. So let me clear this first. So now let us discuss about AC generator. In order to save time, I have drawn this figure before the video is started. Before I have started this video, okay. So here you see a coil. This is a coil having n number of turns. Okay. For simplicity, I have drawn only one turn, right? So let us assume there are n number of turns in this coil, and it is called armature. Let it be A, B, and C, D. So A, B, C, D is called armature, and it is kept between the two poles of magnet, north and south pole, so that this is the direction of magnetic field. This is the direction of magnetic field, DC. So magnetic lines of force are going in this direction through this coil from north to south, right? This is the conventional direction. Emerge from north, merge at south, right? Now here you see, and this coil is being rotated with angular velocity omega. It is being rotated in this direction. So this AB arm is pushed downward and it is pushed upward. Right, in that way. Right. Now what will happen when this is pushed downward and this is pushed upward, and what will be the direction of induced current? So due to the rotation of this coil, magnetic flux across this coil will be changed, and due to change in magnetic flux there will be an induced EMF, and to determine the induced EMF we use Fleming's right hand rule. So how to determine that? So here you see the direction of the magnetic field. Direction of the magnetic field is the first finger, forefinger you can say, and this AB. First let us determine the direction of the EMF induced current in this arm AB. So this is the direction of magnetic field, and it is pushed downward. This thumb represents the motion of the arm, and now this middle finger is pointing towards you, right? That is perpendicular to the board, outward direction, in this direction. So in that case, so that means in this diagram, this coil is in this way, like this. So perpendicular to the board. So here is the direction of induced current. This is the direction of induced current. So let me show you. So it is pushed downward. That is the thumb, and direction of the magnetic field. This is the first finger, and this middle finger. Here you can see this middle finger is the direction of current. this is the direction of current, and it is moved downward and it is moved upward, so in opposite direction. So it is moving in opposite direction. So that's why definitely here the direction of induced current will be this, because magnetic field in both cases are in the same direction, right? But it is pushed downward, it is pushed upward. If it is pushed downward, then if this is the current, direction of current, then here direction of current will be opposite. Now you see, after completion of half cycle, so here you will get CD arm and AB arm will be on the right side, right? Here is that. So this AB arm goes to that side and this comes to that side, this side, right? Now in this case, after half cycle, AB will be pushed up, CD will be pushed down. Now in the direction direction of induced current in AB is in this direction and in CD in this direction. So after a half cycle, you can see clearly the direction of this current is changed. Okay, it will be changed after every half cycle. And here you see these two rings. There are two rings. Okay, these two ends of the coil are linked with these two rings, so that these two connections it doesn't allow these two connections to make twist like this. And there are two brass rings, and these two slip rings works as commutator. Commutator means which change the direction of current in the circuit after half cycle. So here you can see in AB, in the first situation, it is in this direction. The current, induced current, is in this direction, and here when AB goes to that side, direction changes, and so on. It will rotate this way, and the current produced will be AC as this direction of the current is changing after every half cycle, right? So hope you have understood this. So if you see, let me tell you something here. So what will be the if let me tell you, suppose theta angle is being this coil rotates through theta angle in time t, then angular velocity omega is given by theta by t, and that's why theta will be equal to omega t, right? Now flux in this coil, if there are n number of turns is n number of turns. Right? If there are n number of turns, then magnetic flux linked with this will be n b dot a, right? N b dot a vector. So b dot a, that's going to be dot product of these two vectors will be b a cos theta, and theta is omega t put here. Then our phi will be, this phi will be equal to n b a cos omega t, since theta is equal to omega t, right? So what will be the induced EMF? Induced EMF E is equal to minus d phi by dt. Now as there is n turns, don't take here n, because n is already taken here. Clear? So you may think that there are n number of turns, so we should take n here, but we are not going to take n because this is already taken here. After that, this flux is used here. Okay? So hope it is clear to you. Now here you can see, let us replace this flux phi, this phi, where this value of phi put here, then what you will get? Minus d by dt n b a cos omega t. So we have to differentiate this term with respect to dt, and here you can see cos omega t is the function of time only. right? Cos omega t is the function of time. So that's why we can write E is equal to n minus nba d by dt of cos omega t. And we know derivative of ddx of cos ax is minus a sin ax. So I hope you have got this one in mathematics, in derivative, right? So then after differentiation with respect to t, what we will get? nba omega, sorry, not only omega, minus sin omega t, omega, minus omega sin again omega t. Now consider this a as omega and t as this x. Here we are differentiating with respect to t, isn't it? And in that formula it was x. Okay. So E is equal to, so minus minus plus, so finally this is the answer, sin omega t. Now here you see the maximum value of sine function. Always remember value of sine theta for any value of theta. Its maximum value is 1 and minimum value is minus 1. Remember it. Maximum value is 1, minimum value is minus 1. So when EMF will be maximum? When sin theta is equal to 1. Okay. Then sin theta, when sin theta is 1, when theta is 90 degree. That means area, angle between the area vector and magnetic field must be 90. So that maximum flux will be passing through this surface. Then this one will be maximum. So that's why what we can write here, we can write maximum value of sin omega t is equal to 1. Therefore maximum induced EMF, maximum induced EMF will be, let us consider the symbol as E naught. So if this is equal to 1, then what will be E naught NBA omega. So this is the maximum induced EMF. So in this expression, here you can see this NBA omega, this part can be replaced by E naught. Then this formula becomes E is equal to E naught sin omega t. So this is the final expression where E naught is maximum induced EMF. So hope you have understood this. Now if you draw the graph, so now let me clean this part. So board is very small inside. So now here you see, let me take this. Now I have already told you that maximum value of sine function is 1 and minimum value is minus 1. So if you draw the graph of EMF with respect to time t versus E graph, so it is a function of sine, and this is maximum value is plus 1 and 0 and minimum value is minus 1. Then if you draw the graph of this, then you will get graph EMF versus time, then you will get such graph. Right, this is called sinusoidal graph. Okay. So hope you have understood. This is all about AC generator. How does it work? Okay, and this chapter is completed, I hope. So thank you for watching.